Okay, so on to an application of some of the ideas that we talked about last time. So first, a very quick reminder. Notice the attendance code down here. Don't forget that we still do have quizzes. It's just that now the quizzes are only checking attendance. So enter this number as the answer to the quiz on Sakai for today's date. Okay. All right, so again, you can do that anytime during the lecture. The quiz opens 5 minutes before the lecture starts. The quiz closes 5 minutes after the lecture is scheduled to end. So, there you go. Okay, so nice application of some of what we talked about last time. This goes back to linear differential equations from Chapter 4. Recall that we made the assertion that the set of solutions to the homogeneous equation was an n-dimensional vector space, and I did not prove that at the time. I made a statement about how, well, the book's proof is unwieldy, and there's a lot of work that goes into it, and it's going to be so much easier when we have more powerful tools from Chapter 5, which we now do. So let's prove this result. How do we know the set of solutions is n-dimensional? So we'll start off with a couple of observations. First of all, we already know the set of solutions to this differential equation is a vector space, right? And now here's a different observation. This doesn't immediately seem like a natural thing to want to do. Ends up being very valuable. The set of initial values that you could use as in connection with that differential equation, also a vector space. In fact, it's a familiar vector space. If you think about it, what initial value is it's what is y of 0, what is y prime of 0, etc. It's a collection of these values in values and derivatives of the solution in question in order. It's an n-tuple, right? It's an ordered list of n numbers. It's a vector in Rn, right? So every one of these initial values is also an element of Rn. Well, of course, Rn is a vector space, right? That's not. If you think about it, it's not really a new observation. The only new observation is that you can think of initial values in this way. Okay. So we have two vector spaces. We have this set of solutions, and we have this set of initial values. So here's the tricky idea. Here's the Chapter 5 idea. What we could not have done in Chapter 4 because we didn't have the tools is I'm going to define a linear transformation from, let's see, I have some color choices. Bear with me for just a second, purple and blue. Okay, so from the collection of solutions, that's a vector space, to the collection of initial values, that's a vector space. I'm going to define a linear transformation from the purple vector space to the blue vector space, and the formula is plug in, basically. In other words, given a solution, given some element of this domain vector space S, given some solution to the differential equation, my output value is what are the corresponding initial values. Right, so take the appropriate derivatives and plug in t equals 0. It's not hard to check that this is a linear transformation here, and so this is something I'd like for you all to do to check that that is a linear transformation. Nice exercise. Not unlike several of the exercises that we talked about last time. Right, how do you check something's a linear transformation? Okay, so what do we do with this linear transformation? So, by the way, I have a visual aid for this that's not in the lecture notes. This is something that I wrote afterward. This is on Sakai, right, in the resources section, so you can download that at your convenience. This is just a way of kind of visualizing all this setup that we just made. So let me start off with what is S? Well, we have this collection of all solutions. There it is. For example, I should say, this is an example of what a solution looks like. Right? It's y is a function of x. Okay. What does an initial condition look like? Well, we had this conversation a minute ago. Right? An initial condition, initial set of initial values. I'm writing it in blue there. Is, at x equals 0, it's what's the value of the function, what's the derivative of the function, the solution in question, all the way down to the n minus 1 derivative. And again, this is just a bunch of values. So there's a bunch of numbers here in order. That's a vector in Rn. Okay. So our function that I'm defining here, that I have in red, this linear transformation from S to I says whatever solution you want to talk about, the output is what's the initial condition that it came from. Okay, again, defined by that formula. So back over to here. Here is that linear transformation. Oh, whoops, and I forgot to, whoops. There we go. Okay, so given a solution to the differential equation in purple, as an input, the corresponding output is what is the corresponding initial values. Okay, now what do we do with this linear transformation? I claim that this linear transformation is 1-to-1 and onto. I claim that this is a bijection. So we talked about this last time. Let's see here, up here. Yeah, here it is. 1-to-1 and onto. Bijective, meaning that it's a perfect pairing. That for every output from this linear transformation, there is exactly one corresponding input. You never have two inputs that give you the same output, and you never have any output that doesn't come from any input at all. So there's perfect pairing 1-to-1 and onto. Okay. Now, how do I know that this linear? Where did I put my? Oh, here it is. How do I know that this is 1-to-1 and onto? And I claim that both of the required things that we have to check are immediate consequences of the existence and uniqueness theorem. And we just have to kind of think this through. I'm going to think it through over on this other page here where we have these kind of pictures drawn. How do I know for every wrong color. Sorry. How do I know for every output there is exactly one corresponding input? Okay, let's say that a little bit differently. How do I know that for every initial condition, how do I know that there is exactly one corresponding solution? Well, because that's exactly what the existence and uniqueness theorem says, right? Certain conditions being satisfied. For every initial condition, there is exactly one corresponding solution. Okay, so for every output in I, there is exactly one corresponding input in S. And that means that this is a 1-to-1 and onto linear transformation. All right, now why do we care about that? This may ring a bell. This corollary that we were talking about, where 1-to-1 and onto came up in the first place. The punchline of this corollary is if you have a linear transformation that's 1-to-1 and onto, then the domain and the target have the same dimensions. Now, what does that buy for us? Well, let's go back to where we were over here. Knowing that this linear transformation is 1-to-1 and onto, I know that this domain and this target have the same dimension. Okay, let's think that through. The dimension of S is what we're trying to figure out in the first place. We're trying to understand the dimension of this vector space of solutions. The dimension of I is obvious. We've already agreed. The set of initial conditions is just Rn. The dimension of Rn. Old news. It's in. Right? So that gives us the conclusion that we want. The dimension of the set of solutions is in. It's as quick as that, right? So there's just a few things. Most of this argument is set up. Most of this is making sure that you understand what is this function t, confirming that it's a linear transformation. Again, I'm leaving that as an exercise for y'all. and then just observing, without any necessary algebra, that this satisfies all the conditions of the theorem on the previous page, and again, it's a kind of a free result. Okay, so I think this is much nicer than the book's argument back in chapter 4. If you look at how the book proves that it's an n-dimensional vector space, take a look at it. Right, it's pages of clunky setup and checking a bunch of details, much more opaque and unintuitive. I think this is really satisfying. Okay. All right. Does anybody have any questions about this before I go on? Is everybody happy? Okay. It's a little bit of a sophisticated argument. Might need a little bit of time to digest. Might need to listen to the recording to let those ideas, give multiple opportunities for those ideas to make it into your head. But makes a lot of sense, I think. Okay. By the way, quick reminder before we go on: don't forget about the attendance code. Make sure to get that put in on Sky while class is still going. Okay, on to a new section. This is section 5.2 now. So we talked about linear transformations, and we know linear transformations are functions. Right? They're functions that satisfy certain properties, like the linearity condition. We're going to think of linear transformations now in a slightly different way. It's going to seem sort of pointless and arbitrary for a little while here, until at the very end of today's lecture, as long as I move fast enough, we're going to prove some really powerful results, sort of unexpectedly. Also, kind of going back and filling in blanks on that we left as we were moving along through previous discussions. So in chapter 4, there were some big blanks of how do I know this theorem is true. We're going to fill those in today. But like I say, it starts off seeming a little bit arbitrary. Even though linear transformations are functions, let's choose to view them as objects, elemental little things that I can add or multiply or something. Now, we've done something like this before. Let me remind you, we were talking about matrices, right? So you can think of a matrix as being, it's a bunch of numbers arrayed in a certain way, and it's a shorthand for a linear transformation. And then we made the observation, but you could develop an algebra of those matrices. You could talk about what it means to take a matrix and another matrix and add them. Or what does it mean to take two matrices and multiply them, right? We wrote down some formulas that we, to be totally honest, still haven't really justified very well. So even though we were thinking of them in one way, we could choose to view them as on their own elemental little things with which you can do operations. So we're doing the same thing here, just now linear transformations instead of matrices. So here's a couple of formulas. If you give me a couple of linear transformations, I'm going to tell you here about what it means to add those two linear transformations. Right? What does it mean to take this function, which is a new kind of an object, right? This isn't it's not a number, right? It's not a vector exactly, at least not in the Euclidean sense. It's a linear transformation. So this is a brand new operation that I'm about to define. What does it mean to add two of these new kinds of objects? And here's the formula. If I'm going to tell you what this new function is called t plus s, the way I tell you what a function is by telling you how to evaluate it. If you want to know what t plus s is, evaluate it at the vector v by way of this formula. That's what t plus s is. Right? This gives you an understanding of what this function is because there's a formula for how to compute it. Okay. All right. Now, awkwardness about this equation. What's going on here? Don't forget, we're defining this symbol. We're defining what plus means. This is a brand new operation that we've never talked about before until today. What does it mean to add two linear transformations? And a very unfortunate and awkward bit of notational choices, that right there, right, the same little symbol, this is not the same operation. This is something we've already talked about. That's the addition operation in W. Right, think about it. T and S both have W as their target. that means T of V and S of V are both vectors in W. And if you have a vector in W and another vector in W, what it means to add those vectors in W, old news, right? Vector space addition, we talked about that a while. Okay, so again, a little bit awkward. Heads up, you always have to be on the lookout for this in this kind of situation. Always think about when you see this symbol, you have to think about, whoa, hey, what is this? What am I adding? Apparently I'm adding two things. What are these things I'm adding? And don't inadvertently conflate possibly two different uses of the same symbol, such as here. Okay. All right, so very similarly, how do you multiply a linear transformation, T, by some scalar, K? Well, again, I'm going to tell you what this new function is by telling you how to evaluate it. There's the formula. Again, there's a confusion of notations. This is brand new. Scalar times linear transformation is what we're defining here. This, again, T of V is a vector in W. So this is scalar times vector in W. This is the old scalar vector product from this vector space W. Okay, so again, heads up, always think about the notation. You've got to look at the context, see what are these objects, and interpret accordingly. Okay, so now how are we going to multiply two linear transformations? You would maybe think possibly, well, let's just use the multiplication from W. And then you have to pause and realize, wait a minute, we don't have one. Right? There is no vector-vector multiplication in a vector space. We have addition, and we have scalar vector multiplication, but there's no vector-vector multiplication in a vector space. Not part of the definition of a vector space. So you can't use a strategy like this to define multiplication. What you can do is make this definition here. This is going to seem like a pretty arbitrary choice. I guess it is. But it turns out that with this choice, some really natural things happen. So we're going to go ahead and follow down this road, even though it seems like it's not clear what the motivation is here at this moment. But here we go. If you want to multiply two linear transformations, S times T, all right, the definition. Now, again, I'm going to tell you what this function is by telling you how to evaluate it. The way you evaluate this function st is by way of the composition. In other words, you're going to, if you want to plug v into s times t, first plug v into t, and then whatever comes out, that's what you plug in to s. Okay. All right. So I hope everybody remembers, by the way, this notation for composition, the little circle. Everybody remember that from single variable calculus days, learning the chain rule. I hope you all have all seen that. Okay. All right. Okay, a little bit of work to be done. You do have to confirm that this is also a linear transformation. That's a good little practice problem, something to try. But it is true, this is a linear transformation. Another detail, now you got to be careful with this. These objects that come out of T, according to this setup, those objects that come out of T live in the vector space called W. Well, wait a second, am I actually even allowed to plug that in to S? Well, yes. Right, so this is an important, I'm going to call it coincidence. We need for the target of T to be the exact same vector space as the domain of S. I need to know that what comes out of here has to be something that's allowed to go in to here. Otherwise, I can't put it in, and the whole thing crashes and burns and doesn't make any sense. So that is a requirement in order to multiply linear transformations. Okay. All right. All right, so there's our definition. We've now got the makings of an algebra of linear transformations, right? Let me just remind you, this is not that different from what we did with matrices. We started off with matrices being just a notational choice. Write the numbers like this in this way, and it's just kind of a convenient shorthand. And then we defined addition and scalar multiplication and multiplication. We had the components of an algebra of matrices. We wrote down algebraic properties of matrices, and then from that we can actually do algebra with matrices. We proved theorems with this algebra of matrices. All that business about elementary matrices is done using algebra. The algebra that we define for matrices, right? So it was seemingly an arbitrary thing when we first set it up, but big results come out of having created that algebra. Now we have a new algebra, this time of linear transformations. And again, big results are going to come out of this, as it turns out. Okay, so a little bit more to check. Here's a bunch of great news. A bunch of true facts about this brand new algebra we just created. That addition that we just defined is commutative. Now, there's a temptation to say, well, come on, additions... Again, didn't I prove that in elementary school? No, that was for real numbers. Then we talked about vector addition. That's also commutative. Then we talked about addition of matrices. These are all different addition operations. This is a brand new operation, addition of linear transformations. So it has to be confirmed that it actually is commutative. And in good news, it is, just like you would hope. Likewise, it's associative, and there's sort of a scalar associativity, and there's a couple of distributivities of different sorts. And there's a bunch of true facts about this new algebra. And I think I saw a hand in the back. I'm sorry, I was right in the... Yeah, go ahead.
The target of P must be the domain of S.
Yeah.
Point.
Yeah.
Does it be the entire domain of S, or does it entirely contain?
Yeah, I like for them to be the same, just for kind of simplicity's sake. You can make a definition with it being only contained inside of. We don't have any need to broaden the definition like that in this context, so I'm just going to keep it simple. Yeah, great question. Yeah, you could do that. Let's not, is my answer. Yeah, right. Yeah, right. Okay, so great news. Here's a bunch of algebraic tools that we get to use while we're using our brand new algebra that we just created. Okay, I'm going to prove one of these just to show you how such a proof would work. Before I get to that, I do want to point out what is conspicuously missing from this list, though, and that is multiplication is not commutative, which is pretty, oh gosh, let's call it weird, because, I mean, multiplication, come on, we've seen different kinds of multiplication in different contexts. We are pretty accustomed to multiplications being commutative. Okay, except for matrices, right? So this isn't a completely foreign concept. We have seen multiplications not be commutative. So here we are again, heads up. This algebra is not multiplication commutative. So as you're doing algebra of linear transformations, don't just do this free, like it's legal, because it's not. Yeah, everybody on board? Now, so again, I want to prove one of these facts just to show you how to do it. I'm going to show you how to prove this one arbitrarily. Whatever, they're all kind of comparable in terms of how to prove. So I'm going to show you how to prove this one, and then my suggestion to you guys is that y'all prove, maybe not all of the rest of them, but just prove a couple others. Pick out a couple and write out what those proofs would be. They're going to be very closely modeled on what I'm going to show you here, right? But nevertheless, good exercise to do a couple of those out. Okay, so I want to show that that's equal to that. Right? Keep in mind, R, S, and T are all functions. They're linear transformations. Right? So this sum and then this product of this sum, this thing here is a function. Likewise, this thing down here is a function. I would like to show you that these two functions are equal. How am I going to show you two functions are equal? I'm going to plug in the same thing into both of them and show that you always get the same output. Right? If you have two functions, but whatever you put into both of them, you always get the same out, well, they have to be the same function. All right, so this is just straight up computation. There's kind of no tricky curves on this. It's just a matter of slowly and carefully. Notice here, we have a product. How do you evaluate a product? Well, we have a formula here. A product is evaluated by composing. That's the definition of multiplication here. So, okay, so I compose. So V first goes into T, and whatever comes out, that then goes into R plus S. Right? I am in other words, I'm doing this multiplication explicitly by composing those functions. Okay, that's straight out of the definition. Okay, here's another simplification I can do. Notice that here I have a sum of two linear transformations. What does that mean? How do you add two linear transformations? Well, go back to the definition. The way you add two linear transformations is you plug into each one separately and then add the output values. That's what that says there. Okay. Okay, so I'm going to take this. I'm going to plug that into each of R and S separately. Right, there they are. And then add the output values. So that's straight out of the definition. Okay, so this entire first line up here, nothing's happened except I've just followed the instructions, I followed the rules that we set out for ourselves in these definitions. I just rewrote the left-hand side using the definitions of those operations. Same deal here. Right, just rewrite what you have on the left-hand side based on how these operations are defined. Here you have a sum. You evaluate a sum by plugging into each of those summands separately and then adding. Right? And then likewise for the resulting products. So straight out of the definitions. And then as desired, you notice that that and that are exactly identical, and therefore we're done. Therefore, these two functions are equal, which is what we wanted to show. Okay, so that's one of the proofs. The remaining 8 are pretty much the same thing. Don't feel the need to do all of them. I encourage you to do at least a couple of them. Just pick 2 that look interesting and give it a try. Follow the pattern. It's going to work out just fine. Okay. All right, so there's our algebra. All right, now we're going to prove some big theorems now. And the way we're going to prove these theorems is by setting up a framework. This does take a little bit of time. We've just got to get all these things defined and observed, and then great things are going to happen. So starting off, here's a couple of linear transformations. This one we've already talked about, the act of differentiation. Right? Not the result of differentiation, but the act of differentiation is a linear transformation. We talked about that last time. No problem. Here's another one. This a little bit weird looking. Not a lot's happening here. All this is saying is that the act of multiplying by some fixed function g, that act is linear. And again, not really surprising. Now you do have to keep in mind that I'm not saying that this result is linear. Certainly not. Probably not. Right? What I'm saying is if you view f as being a vector in that vector space, and if you view the act of multiplication by g as being a something you can do to vectors in this vector space, that act is a linear transformation. Easy to check. Great practice problem. To make sure that you're interpreting this correctly, give it a try to show that this is a linear transformation. It should go through very, very straightforward. Yeah?
So, is that first one implying that the derivative of any function is
notice that we're restricting our attention on this first one to C infinity functions. And if a function c infinity, to keep in mind that means it's infinitely differentiable. So I mean, there are a whole bunch of questions of what if I define D on a larger vector space of less regular functions, and I don't want to. There's no need for us to deal with that, so I'm going to make our lives simple and just assume everything is c infinity. Yeah, good. It's a great question. Yeah. Okay. Here's a pretty significant idea. Y'all remember this thing. This is our object of study in Chapter 4. How do you solve these kinds of differential equations? And we've interpreted the left-hand side, everything that you do to y, the process of taking your y, taking various derivatives, multiplying by various coefficient functions, and then adding up these various terms. We've already shown that that is linear, right? So we've shown that these are, thus the name, linear differential equations. Here's the new observation. That linear transformation, L, the action of the left-hand side in these differential equations, can be thought of in terms of these above two very simple linear transformations. Right? Everything that happens in L is some combination of differentiating and multiplying by stuff. Right? So, not hard to confirm. Right? Let's just think about this a few terms at a time. What is this? A little bit of algebra here. What does that do to a function y? Well, what does that do to y? This says we're going to take y, we're going to compute in derivatives of it, and after having taken in derivatives, we're going to multiply by this function called qn. That's exactly that term. Right? Etc. for all the other terms. So, this is kind of a new observation. Even though we thought of L as kind of a shorthand for the linear, for the what happens on the left-hand side of a differential equation, we can break that down into more elemental things. Those being D and this T thing that we defined. Okay. All right. A notational observation. I claim that I can rewrite that as that. This is just a notational choice. Keep in mind this thing here, T sub Q. All that says is this represents the process of multiplying by this function Q. So how would you interpret what I've written here now? And let me confess that this isn't something that I've defined yet. What does it mean to multiply a coefficient function times a linear transformation? Haven't defined it, right? But if you think about, what would this? How would you interpret, q of x dn y? Well, you would interpret this as being the nth derivative, and then times q of x. Which is exactly what I want. That's exactly what I would have. That's what this represents already, right? So it's a nice, convenient notation to just kind of ignore the t part of this notation and just write it in terms of what it actually is doing. This t business serves a function. It serves a role up here to emphasize that we are talking about linear transformations. That we're rewriting one linear transformation in the algebra of linear transformations. Having served that purpose, this is kind of clunky, and so it's much more desirable to go with that. Okay. All right. So we're looking for a homogeneous solutions to a homogeneous equation. That means we're looking for the kernel of a linear transformation. We've talked about that previously. Here's a really weird observation, and again, this seems to come out of nowhere. I was always uncomfortable with this when I first saw it because it just doesn't seem to even make any sense. P of D. Whoa. Okay, hang on. P is a polynomial. P is the characteristic polynomial, right? And we've done a lot of stuff with characteristic polynomials. You write them down, you factor, you find roots and that kind of thing. But in all those uses, being as it was a polynomial, what goes in to the polynomial? Numbers. Right? What's this? What does it mean to put a linear transformation into a polynomial? Can you do that? Can you just put anything into a polynomial? What about a bicycle? Can you take P of a bicycle? Is this just fair game to write down anything that you feel like? Right? Did everybody see what I see? Did everybody see the worry? Right? So, what does that mean, P of D? Well, let's think about polynomials for a second. What do polynomials do? Let me just write down, so P of lambda is, and then it's going to be something like, AN lambda to the n plus blah, blah, blah. Okay. What do you have to be able to do to make sense out of this? Well, whatever you want to put in here, whatever this thing is that you want to put into a polynomial, you just got to be able to do what the polynomial tells you to do. So this thing that I'm putting into it, I need to be able to multiply it by itself. And I need to, whatever the result is, I need to be able to multiply by scalars. And then I need to be able to add various of these results to each other. Can you do that with D? Yep, no problem, right? We know how to multiply D times D. D is a linear transformation. Multiplication is just composition, no big deal. So we can totally multiply D by itself. We can multiply D by scalars. We can add these things to each other. There is nothing stopping us from doing what the polynomial will tell us to do if we put D into that polynomial. And of course, we can't with a bicycle, right? I can't multiply a bicycle times itself. That does not make any sense. That we have not defined such a thing, so that really would be nonsense. This is not nonsense. This is just, an idea that never really occurred to us before. And that's totally fine. Okay. All right. Now, so just because this is not garbage doesn't make this equation true. How do I know that the equation is actually true? Well, let's write this down. L. Here's L. But we're looking at the constant coefficient case here. So L in the constant coefficient case is, let's see here. It's AN D to the N plus AN minus 1 D to the N minus 1 plus, plus A0. That's what L is. Now let's ask, what is P of D? Okay, let's see here. P of D. I need to plug into that formula. I need to plug in D, and I get, let's see here, AN D to the N plus AN minus 1 D to the N minus 1 plus A0. And sure enough, it's just a direct observation. Those really are the same thing. Weird, but easily confirmed. Everybody good? Now let me just take a moment to recognize how sophisticated our machinery is getting here. We started off defining just, for no particular reason. Let's just talk about what it means to add linear transformations. Let's talk about what it means to multiply linear transformations. And now we've got this really powerful observation that the left-hand side, the action of the left-hand side of a differential equation is the same as interpreting the characteristic polynomial acting on the D operator. This is weird and sophisticated. Here's another thing. L, the action of the left-hand side of a differential equation, we can think of as an algebraic process. There is an algebra inside of L. L is not just made up elementally of simpler operators. There is an algebra it makes it up inside of L. Yeah, did you have a question?
So something that I'm a little bit confused about is that.
I'm sorry, I couldn't hear.
Oh, so I guess the way that I see it is that we learned L as an operation.
Yeah.
That we would use on Y.
Yep.
So could you?
Yeah, so
write
P
that?
of D is something that you can do to Y.
How would you write that?
Yeah, well, so here it is. P of D is all this stuff over here. Right? So each one of these terms is something you can do to Y. Like, let's take this one here. You can take Y, you can take derivative in times, and then whatever your result is, you can multiply by this number, isn't it?
So would it be D of Y? For example.
So D of Y would be the first derivative of Y. Now this says, in times, right? You're going to D to the power of n means you're going to compose in different differentiations. That means you're going to take in derivatives in a row. And when you're done, multiply by 8. Yep, and that's exactly what the first term of the calculation is when you write down L. Okay. All right. Now, here's some bad news. Every so often stuff doesn't work out. Again, multiplication does not commute. Right? So, for example, you can't expect these two things to be the same. D times T, T times D. Multiplication of linear transformation. When you compose functions, it matters which one's going into which one. Right? E to the power of sine x is not the same as sine of e to the x. It really matters which one's going to which. So, you wouldn't expect this to work out, and it doesn't, right? Easily confirmed. If you multiply by g before you take the derivative, you get a product rule. But if you take a derivative and then multiply by g, you don't, right? So, oh well, different. Here's where it comes back to good news. Keep in mind, we're interested in the constant coefficient case primarily, at least in this class. Well, most of what we're interested in is constant coefficient. So, if the coefficients are constant, if g is a constant, then notice here, we're taking a derivative of a constant. This whole term goes away, and you do get the same thing either way. Right, so this is now, again, I cannot emphasize enough, this is only if you have constant coefficient equations. But we do, so yay, right? So as we go forward studying constant coefficient, by the way, this abbreviation here, CCLDO, constant coefficient linear differential operators. So L from chapter 4, right? They commute. Okay. So that ends up being the last really important piece of an important puzzle. I claim that we have at our disposal the right to factor these polynomials. Remember, L, we've already agreed, L is P of D. Right? We wrote that down. One term at a time, these are doing the same things. And the new observation that I claim is that you can rewrite that polynomial of D as a factored polynomial. And again, not exactly 100% obvious. Let me show you the little sticky issue there. And I like to just show this with an example. But if we had, D minus 2 times D minus 3, let's multiply this out. You get D squared minus 2D. Now, there's a temptation to say minus 3D, but whoa, slow down. The D is on the left, the 3 is on the right. I really have to say minus D3 before I know that they commute. Right, and then finally plus 6. So what is it that allows you to make this, what is it that allows you to rewrite this, and therefore the product, like that? What is it that allows you, therefore, to factor polynomials? The thing that allows you to factor polynomials is knowing that you can make this switch, knowing that stuff commutes. Right? So, again, good news. That's what we found here. These things do commute, and therefore these polynomials of differential operators factor, just like regular plain old high school algebra polynomials, which is awesome. Okay, so this gives us the tools that we need to get some neat stuff done. I'm only going to show you one of these. There's three big results that I want to talk about. I'm going to show you the first one today. We won't have time for the others, I don't think. Probably. Anyway, here we go. Chapter 4. Right? Recall, we were looking at this differential equation, and we talked about a way to find those solutions. I hope you all might remember where we got the characteristic polynomial from in the first place. And that is, we took a wild, baseless stab at maybe this will work, right? We took e to the lambda x. I don't know where this came from. We just, for lack of any better ideas, we tried, maybe exponentials work. We plugged in e to the lambda x, and out came this lovely argument about the characteristic polynomial, and whenever that's 0, then, hey, it does work, right? Well, what's the justification, right? Other than, well, it worked, so, the ends justify the means. Is that okay? Is there a different justification for why did we try exponentials? And the answer is, yeah, there's a lovely justification. Here's the idea. L is P of D, which factors. Right? This is a new idea. We could not have talked about this in Chapter 4. This L is not just, a shorthand for this process of various derivatives you take. L is an algebraic object that can be broken down in linear factors like this, all of which commute. So I could, because they commute, I can rewrite all of this business by taking one of these factors, pulling it over to the right, and then all the remaining factors, all of these remaining factors, other than that one that I pulled out, we'll put over here. Call that, I'm just going to call it Q of D. It's some polynomial in D. It doesn't really matter. Okay, so trying to solve this equation, aka this equation, comes down to solving this equation. And now we can make this really clever argument. Can I think of any instances in which this equation works? Well, how about this? Notice if I could ever make this first part, if I could make this 0, right, let me do it like this. If I can make that 0, that will be a solution. No guessing required, right? I mean, if my function y, whatever this function might be, if when I apply d minus ri, if the application of this gives me 0, it doesn't really matter how many other derivatives I take, right? If this is 0 right here in yellow, all the derivatives in the world, still 0. Multiply by whatever coefficient, whatever, still 0. Add as many of the terms as you like. You're adding a bunch of zeros. So, of course, it will still work. Right? So we don't have to guess. Hey, maybe, possibly exponentials might work. I know for sure that anything that solves this differential equation is going to work. And not hard to confirm, that differential equation is the same as that differential equation. This, by the way, you'll recognize as the natural growth equation. And that's the solution. Right? So this is a motivation for why it was not such a bad idea to try exponentials in the first place. Had we not had the good fortune to have guessed exponentials, this analysis would have gotten us down to exponentials by itself. Everybody happy? Okay, just a little bit of a preview of what's coming up on Friday. Recall there was this question of, how do you know that multiplying by x to the k, various values of k, when you have a repeated root, why is it that multiplying by powers of x will give you the additional homogeneous solutions. We're going to prove that next time. And then another dangling issue from chapter 4. When you're looking for particular solutions, why the x to the m? Why do you multiply the naive guess by this magic x to the m? Why does that work? I'm going to show you that next time. See you later. Have a good day. Just come talk to me. Yeah. Okay. See y'all later.